Alright, so for this problem, we're going to be dealing with a situation in which we have a cylindrical container that has some amount of liquid in it. Now this cylindrical container has a cross-sectional area of AC and a height of capital H. The liquid initially has a height of H initial, and then just the liquid level in general is going to have a height of lowercase h. So we have this container, we've got an initial pressure inside here of atmospheric pressure, so 101.325 pascals. The exterior pressure external is also atmospheric pressure, and that's just the pressure surrounding the entire container. And then we have a hole gets poked, small hole, at the bottom of this container. And so this liquid is obviously going to start flowing outwards. So as it flows outward, we're going to assume that this hole is small enough that air can't get back in. And so we're going to be wanting to find a relationship between the change in height of the liquid over time. And in general, from experience, we can know that this will look something like that, where it eventually flatten out and stop altogether. So we're looking for this relationship, and we're going to note two important points for this, and that's one right here on the surface of the liquid, and two, which is like right at the hole. All right, so what do we know about this situation? We know that the pressure inside here is originally atmospheric pressure, and then as liquid starts flowing out, the volume of the liquid is decreasing, which means the volume of the air inside is going to be increasing. And we know from the ideal gas law that as the volume increases, the pressure is going to decrease. But since there is no air getting back in and no air escaping from the container in any way, we know that the number of moles of air that we have is going to be constant throughout the entire process. So we can use the ideal gas law to solve for the number of moles that we have. So ideal gas law is PV equals nRT. And in this case, we're going to assume that the temperature of the entire system is constant and it's not going to change. So solve for moles, we have N is equal to PV over RT. So N equals 101.325 times the volume. So the volume is going to be this cross-sectional area times this height, which is big H minus the initial height. Because this is the initial pressure, so we're going to use the initial height for this. And then that is divided by RT. So that's the number of moles that we have. So we can go ahead and plug this right back into the ideal gas equation, but this time we're going to be looking at specifically position 1. So for that, we're going to have that the pressure at 1 times the volume is equal to N RT. Alright, so then pressure at 1 is equal to N, which is this, 101.325 times cross-sectional area times capital height minus initial height of the liquid over RT, and then that, so that's N, and then times RT, divided by the volume. So this time, this is just the volume at 1, which is going to change based on the height of the liquid. So this is still going to be the cross-sectional area times capital H, but this time it's going to be minus this variable H that is changing. Okay. And from here you can see that the RTs cancel and the ACs cancel. So we've got that the pressure at 1 is 101,325 times height of the container minus the initial height of the liquid over the height of the container minus the height of the fluid at any particular time. So then, after we have that, we can start looking at Bernoulli's equation. So, for Bernoulli's equation, we've got the pressure at 1 minus the pressure at 2. Nope, that's wrong. We've got the pressure at 2 minus the pressure at 1 over rho is equal, I don't know what I'm doing, plus the velocity at 2 squared minus the velocity at 1 squared over 2 plus g times delta z. And that is equal to the frictional heating. In our case, we're going to assume that frictional heating is negligible and we're not going to consider it. So we'll just have that set equal to 0. The other thing that we're going to have set equal to 0 is going to be our velocity of 1. And that's because in relationship to this problem, the size of this hole versus the size of the entire container is going to be drastically different. This hole is very small and the velocity is going to go very fast out of that hole, where the velocity of that top layer of liquid is going to be much slower in comparison, to the point where it's almost negligible. So we're going to assume in this case that it is negligible. Okay. So then we can plug in, we know what P1 is, we can plug that in here. P2 is going to be the same as our external pressure, because this pinprick hole here is a sudden expansion. It goes from this pinprick hole to the entirety of the atmosphere, So that's a sudden expansion, which means pressure is not recovered. So no pressure recovery. So this is also equal to the pressure at that point too. Okay. So we know pressure at 2 and pressure at 1, and we can plug those in. So we're going to do that. So pressure at 2 is 101,325 minus the pressure at 1, which is this, 101,325 times H minus H initial over H minus H all over rho, plus V squared at 2 over 2, and then plus G times, so then this delta Z, that's our change in height, which is just going to be negative H, because this is position 0, this is H, so that's going to be negative, it's going down. Okay, so then we got all that. We can simplify this a little bit. So we can factor out the 101,325 in the row. We get 101,325 over rho times 1 minus capital H minus HI over capital H minus H. And then, yeah, rest is the same. Okay. And we're going to be solving for this velocity value, because that's what we don't know out of this, other than H, but H is changing, so we're going to keep that. And then we're going to solve for the velocity, because we can figure out the density of whatever liquid we have. And we can figure out the height of the container and the initial height of the liquid, that's known. So we're going to solve for velocity. So our velocity at 2 couple of steps. So first we're going to get everything over to that side, so GH, and then minus this, and then we're going to use that negative sign to flip this, the signs in here. So we're going to distribute the negative sign into there, so it will be plus 101,325 over rho times h minus hi, or h minus h minus 1. Okay, so then, keep simplifying, we've got v2 is equal to square root of 2 times all of this, gh plus 101, 325 over rho times h minus hi over h minus h minus 1. Alright, so then we have here an equation for our velocity. So it's still not quite an equation of height or time. We do have height in there though, so that's good. We just need to now relate this to time. So the next thing we're going to look at is the flow rate. So we know that the flow rate going out, so the flow rate going out of here is going to be equal to the velocity of the liquid going out there, so that's the velocity at 2, which is this value, times the area of this hole, so h. Okay, so then we also know that the change in volume, so that's volume, that's velocity. I'm trying to make this one really big. So the change in volume of this liquid here over time is going to be equal to the negative flow rate. Because as the liquid leaves here, as the liquid goes out, it, exits the container, so it's going to affect the change in volume of that container. And then we can also know that this dV, the volume is only changing based on the height, the width stays the same, so that is going to be equal to AC dH. And we plug that in and that in there, so we've got AC times dH dt equals negative v squared area of the hole. So then, now you can see that we've got change in height with change in time, which is what we're looking for over here on our graph. We just have to finish plugging everything in. So we've got dH dt is equal to negative of this value here. That's 2 times acceleration due to gravity times height of the liquid plus 101,325 over the density times height of the container minus the natural height of the liquid over the height of the container minus the height of the liquid minus 1. Okay. And then times the area of the hole. Put parentheses around all of that. Times the area of the hole divided by the area of the container. And so this is a relationship with changing height with relation to time. As you can see, the height, the variable of the height in liquid is the only thing that is changing, the only thing that's unknown. We know acceleration due to gravity, we know the density, we know the heights of the containers and the height of the initial height of the liquid. We can figure out we can measure the sizes of the holes and heights of the containers and everything. So that is our differential equation for the change in height with relation to time. so for the next part of this homework, we're going to use this equation that we just derived that I have copy pasted over here, and we're going to use it to solve this specific problem, these specific values, and we're going to do that using Python. So first thing we're going to do, we're going to import the libraries that we're going to use. So first, import numpy as np, and we're going to use that for basic, arithmetic operations such as like square root and absolute value and that sort of thing. And then we're going to, from scipy integrate, we're going to import solve IVP, and that's IVP's initial value problem, and that's what we have here. It's a differential equation, and where we know the initial value of our dependent variable at t equals 0. So then, from plotly subplots, and then import make subplots, and we're going to, that's what we're going to use to actually plot out our results. All right, so next thing we want to do is we're going to just define all of the variables that we know. So I'm going to take these straight from the problem description. So we know that our height is 1 meter. We know, and then as we do this, we need to make sure we have decimal points that it interprets it as floating points and not integers. So then the area, cross-sectional area of our container is 1 meter squared. The initial height of our liquid is 0.9 meters, and then our initial pressure is 101,325 pascals, and then our cross-sectional area of our hole is 0.001 meters squared. Right. And then other values we need our acceleration due to gravity, so G is 9.8 meters per second squared. And then we also need our density, so it says that we're working with water, so rho is equal to 1/83 kilograms per meter cubed. Alright, so there are our values that we have. And next thing we're going to start working on our solve IVP. So solve IVP takes in a function that it then solves. And this function needs to be defined in certain ways, and it needs to be, like our dH by dt is equal to this whole right-hand side, which is how we have our equation solved, so that's good. And then it also takes in vectors and stuff. I'll show you. So first we're going to define our function. We'll call it RHS for right-hand side. And this function is going to take in our independent variable, which is t, and it's also going to take in a vector of our dependent variables. And you might wonder why we're taking in a vector when we only have one value. It's because solve IVP is set up to handle multiple different differential equations for like simultaneously differential equations. And so it'll take in a vector of every single dependent variable that we have. We just happen to have only one in this problem. So it still has to be a vector though, or else it won't work. So that's not what I meant to do. Alright, so then we're going to unpack the vector into our h. So h is our vector, the first value of our vector, which is 0, because Python indexing starts at 0, not at 1. And then Then we want to return our right-hand side equation. And we're going to also have to return this as a vector because solve IV takes in a vector and it also returns as a vector for the case of multiple differential equations. Alright, so now we just have to type this whole thing in. So I'm going to start with the areas just so I don't lose track of those. And I'm also going to put that negative sign with them. So I have the negative of AH divided by AC. We're going to multiply that by NP dot square roots. This is how we do square roots. And it's going to be the square roots of 2 times parentheses G times H plus P divided by rho times parentheses and then parentheses again, H minus HI divided by parentheses H minus H and then minus 1. Alright, and that should be good. Yeah, I think it looks fine. Okay. And then we'll shift enter on that. Okay, so it seems to have worked. We still don't have any obvious typos right now. So next thing we want to do is we're going to put this into solve IV. And we're going to store our value in a variable called result. So result is going to be equal to solve IVP. And so first thing it takes in is our function. So our function is RHS. Next thing it takes in is our time span. So this we haven't defined yet. We're going to from time 0, obviously, and then until a certain time. And I'm going to put that time up here as t end. And we're going to start with 10 seconds. I'm going to put it up here so that we can change it easily later on without having to go back every time, find every place that we put t end and change it there. So I'm going to put it as a variable up there. Okay. So then next it takes in our initial value. So our initial value, it needs a vector, and our initial value is hi. Then it takes our method, so we're going to use the method rado, and then it will take indents output equals true. Alright, so then shift enter. Yep. Oh, I missed. Let's try again. Alright, there we go. So then, next we can just look at our results. Alright, so it seems to have worked for this. So next thing we can do is we can plot this. So plot, we're going to need to make a plot. So we'll start with fig equals make subplots, and then we're going to do fig dot add scatter, where our x values are going to be right, hold up, let me get, alright, so now I'm back with the lights on. Alright, so our fig add scatter, we need our x values. So our x-axis we want our times, but we're going to need just a list of times. So we're going to have our times to plot. It's going to be equal to np.lim space from 0 to t end. We're going to have, say, 500 points. And then that's interesting because I literally didn't change anything in that. Okay, so it's saying that it encountered an infinity in the square root. I must not have had something shift entered all the way before. Anyway, so it's encountering an infinity in the square root, which means that we have our time n going too long, and so it's getting into like really small values, and it's encountering some round-off error, and that's making the square root negative, which is not a real number, and that's why we're getting this error. So I'm going to see if this works. Okay, so 1 second's fine. I will show you how to fix that here in a second, but I want to finish plotting it first. So our x values are t plot, and then our y values are going to be this result. So we need to know how to get, obviously, that out of here, and it's going to be this solve button. So, so the way we're going to do that, so we're going to do result dot solve, and then what first value of that. We need to put what we're plotting it with. Alright, so then you can see that we get an array of, at all of these times in the t plot, we get what the height is, as it's calculated by the solve IDP. So we're going to take that, those are going to be our y values. I'm going to copy that, put it down here. Alright, I'm going to shift enter and we're going to see what this plot looks like. Alright, so as you can see, I got this error, and that's because I've got the parentheses here. Alright, so now we get a plot, and you can see it's kind of a curve. It looks kind of straight right here, but that's because we have it at such a low time because we were getting that error message from earlier. But it's kind of looks like how we expect it to look. So next problem we have to deal with is the fact that that time was wrong. So we can start by just, manually guessing, and, like I tried 5 and I was like, that does look better. But we don't really want to just keep manually guessing because that's a lot of effort. So one thing we could do is just put absolute value in the square root, because that's where it's finding the error. So let me get that error back just so you can see it. Wrong way. Alright, so array must not contain infinites or not a numbers, and that's because it's getting a negative in the square root. As the value gets closer and closer to 0, there's some round off errors, and so it might go negative, and that's where the issue is coming into play. So one possible solution to that would be to add the lights went out. Alright, so one possible solution to that would be to add an absolute value here. So like that, and then we put another parentheses, and then enter, enter, enter. And you can see that fixes the error of us getting weird numbers, or not weird numbers, like not numbers, but we're getting weird numbers now. We know this is not how this graph is supposed to look, so it's not a complete fix. And so how we're going to fix this is we're going to add an event to our solve IVP, and this event is kind of just going to track when that value goes to 0 and terminate the program. So we'll add this down here. Similarly to right hand side, we're going to have to define a function. We're going to just define a function, we'll call it event 0. It's the first event that we're doing, I guess, I don't know. And it's going to take in the same values as before, of time, and then a vector of our independent variables. So I'm just going to copy that. And then it's going to return, and we want to return this part that we want to go to 0. Okay. So that's the value inside the square root, and that's what we want to track when it goes to 0. So to track when that goes to 0, we're going to do, or to, the function tracks it. This is going to terminate the program, so we're going to call it, put event 0 term, no, equal to true. So that'll terminate the program when that function goes to 0. And then we just have to shift enter on that and add it into here. So we're going to add event equal to, and then it'll take event vector, and our vector is event 0. It takes an event because you have more than one event if you needed to for the problem, but we don't. So I'm going to shift enter on that, shift enter over here. All right, and then this still looks a little bit funky, but that's just us. We haven't fully implemented this yet. So the problem is that the times that we're plotting is still going to t end as opposed to when we terminate the event. So let's add it down here. I'm actually going to copy this out of here because we're going to want that to occur after we put in the solve IVP, because that's after it calculates when this happens. There. Let me just shift enter to there. Right. And then we're going to look at results. Alright, so now we have this value here, t events, and that's the time that the event occurred. So we want to use this instead of t end. So we want to use results dot t events, and then let's just take a look at these. So result dot t events. So that's an array. So we need to get it out of that array. And it's still within an array, so we want to do another one. Alright, and so then we got this time. So we're going to use that value in here. Alright. Then I'm going to enter there. I'm just going to shift enter from the top because I did some weird things. So, alright. And then there we have it. So that is our plot, and it goes until it reaches that steady state point. So that's how we would solve a problem like this. Yep.